Okay, so let's talk clouds here for a little bit. Specifically, what I want to do is I want to give a brief overview of basic cloud types and then talk a little bit about why it is that we get certain types of clouds on some days and then other days we get other types of clouds. And as we'll see, the answer to that is going to tie into this notion of stability that we introduced in the last screencast. Now, I should note that I'm not going to give a very detailed discussion of cloud identification and different cloud types. I'm really just going to focus on the basic types. If you want to see a more detailed discussion, you can read the pages in the text that are listed associated with this lecture on the website. I'm also going to post a screencast on cloud identification that I used to give an older version of the course. So you could watch that if you're interested. But the reality is that we don't need to know all the details of different types of clouds. We just need to know the basic types for our discussion. And so that's what I'm going to focus on. So let's start off then by just going through a basic discussion of the different types of clouds. And it turns out that in terms of the basic cloud types, there's really three different types of clouds. So the first type of cloud is cirrus clouds. And cirrus clouds are clouds that are characterized by being sort of thin, wispy clouds. They're not very substantial clouds. They form very high in the sky. They often just kind of seem to be kind of dusted up there. They're not very thick. They're just not very substantial. So we could define cirrus clouds to be thin, feathery, or wispy clouds that form high in the sky. Now, for each of these types of clouds, over here next to the definition or next to the description, I'm going to give a little just schematic. I'll have pictures of the clouds on the following slides, but for now I'm just going to sketch in a little schematic so you can kind of get an idea in your head, a sort of a schematic idea of what these clouds look like. And so for cirrus clouds, here if I put the ground in here, cirrus clouds are thin, feathery clouds high in the sky, so I'm just going to sort of represent that by this. Right? They're just thin, kind of wispy clouds that form high in the sky. Not very substantial. The second basic cloud type is stratus. Stratus clouds are characterized as being layers of clouds. So they're kind of flat clouds, layers of clouds, flat cloud layers that blanket the sky. So they're the kind of cloud that'll cover a significant portion of the sky. They're relatively flat clouds when you look at them from below, and they just look like a big layer of clouds. So these are the classic clouds that you would find on a sort of a gray sky day. So there are classic gray sky clouds. So if I had to represent that by schematic, it would look something like this. There's the ground again. And stratus clouds are clouds that form in layers that kind of blanket the sky, so they look kind of like this. Right? It would be a layer of cloud that extends over a wide region and covers a significant portion or all of the sky. Okay, so we've got cirrus are thin, feathery, high clouds. Stratus are cloud layers. And the third type of cloud is cumulus clouds. Cumulus clouds are characterized by having sort of a puffy appearance to them. The classic cotton ball cloud is one type of cumulus cloud. And sometimes they can be relatively small, or sometimes they can be bigger. When the cumulus clouds are bigger, they have the characteristic of a plume that's bubbling upward from below. That's actually what they are, basically. They're a plume of cloudy air that bubbles upward from below. So if I'm going to sketch that in as a schematic, it might look something like this. There's the ground again. And depending on conditions, your cumulus clouds can have various depths to them. So In some cases, they may not grow very high, and so they'll be sort of relatively small clouds. Those are our classic cotton ball clouds. We get those all the time here in the summer, day after day after day. We'll have sort of cotton ball clouds that are at a certain level in the sky. They're typically pretty low clouds. And that's a cumulus cloud that just doesn't develop very high. But in some cases, under certain conditions, the clouds can build higher. And in that case, you get things that kind of look like this, that extend upwards. And in this case, they kind of have the appearance of something that's bubbling upwards from below. If you've ever watched one of these clouds develop, you can see that that's kind of how they work. They kind of bubble upwards from below, and then one bubble will come up and sort of die out, and then the next one comes up and dies out. If you go on YouTube and look for time-lapse videos of cumulus clouds, you can sort of see this characteristic of them sort of bubbling upwards from below. So those are our three basic cloud types as described by their form, their basic characteristics. We've got our thin, feathery clouds high in the sky, that's cirrus. We've got layers of cloud is stratus. And then we've got our clouds that are sort of bubbling upwards, and they have a puffy appearance, and those are cumulus. Okay, now let's go through and show some pictures of these things and give a bit more detail about each of the three basic types. So now let's go through and look at some pictures of these clouds so we can get sort of an idea of what these look like in real life. So we'll start with cirrus clouds. I have a couple examples of cirrus clouds here, two different forms of cirrus clouds. And I'll go through and give a few details, sort of a fact sheet of each one of these clouds, just listing some of the important characteristics. So first, for cirrus clouds, where do cirrus clouds typically form? Well, typically when you see cirrus clouds, they're very high in the sky, and in particular, they're up sort of in the upper troposphere levels. So we'll characterize the height of the cirrus clouds as upper troposphere. You can think of that as maybe being 7 kilometers or higher. The depth of the troposphere is like 12 kilometers, so these clouds are going to be up, 8, 9, 10 kilometers, maybe a bit more. So they're high in the sky. Okay. What? And in particular, what are they made of? Well, cirrus clouds form very high in the sky, and that high up it's really cold. And so cirrus clouds are going to be almost entirely made of ice crystals. They're basically all ice crystals up there because it's so cold that the water droplets freeze. And what kind of forms do cirrus clouds take? Well, the classic form of cirrus are wispy, feathery clouds, like this example shown here on the left, where it sort of has a feathery appearance to the clouds. Often it kind of looks like a tail or the mane of a horse or something like that. And the reason for that is basically what's going on is that these ice crystals fall slowly, and as they fall, they might fall into slower air, and so they get left behind because they're falling into slower air. The wind speeds are slower, and so you end up with this tail that sort of extends outward from the cloud. So that's the classic cirrus cloud, but you also see sometimes the clouds sort of have this speckled appearance like shown here on the right. That's a different kind of cirrus cloud. And sometimes it'll just sort of be a very, thin, gauzy layer very high in the sky as well, is also a type of cirrus cloud. But the main point is that these are all sort of insubstantial clouds. They're not very thick. They just kind of look like they're dusted high in the sky. They're all cirrus. Okay, so that's cirrus. These guys are examples of stratus clouds. Stratus clouds. Now, as I just mentioned, stratus clouds are clouds that form in layers. So first, where? Typically, stratus clouds are going to form sort of lower to mid-troposphere. That's where you're going to see stratus clouds most often. Lower to mid-troposphere. So it could just be 1 kilometer or 2 off the ground, or it could be 5 kilometers off the ground, lower to mid-troposphere. What are they made of? Well, in the lower troposphere, they're water. So water droplets in the lower troposphere. As you go up to the mid-troposphere, depending on the season and where you are, your latitude, they often have a bit of ice mixed in there. So in the mid-troposphere, they're often going to be mixed ice and water. So in the lower troposphere, we're looking at water droplets, and mid-troposphere, mixed ice and water. The forms that stratus clouds take, well, stratus clouds are layers. They tend to form in flat layers of clouds that cover part or the entire sky. So it's your typical gray, rainy day cloud. That's your stratus cloud. And you can see that in the examples over here. This is a layer of cloud that's covering the whole sky here. Same as down here in the other example below. It's a layer of cloud that covers the whole sky. This one down here below is raining. So stratus clouds do rain. They're kind of, don't rain hard typically, but they do rain. So those are stratus. When I lived in Seattle for 5 years, where I went to school there, graduate school, and we would have this stratus clouds like this covering the whole sky the whole winter, probably 8 months of the year, every day. These very thick stratus clouds. It was very dark because we almost never saw the sun. So I'm not entirely fond of stratus clouds. And then our third type of cloud here, jumping ahead, a couple examples here of cumulus. Cumulus clouds. Cumulus clouds can take various forms, but they all sort of have this puffy appearance to them, or bubbly appearance, if you like. So first, where? Most of the time, cumulus clouds have their base in the lower troposphere. So the base of the cloud, the lower part of the cloud, forms in the lower troposphere, but then the cloud extends upward from there. Now, how high it can extend upward depends on the conditions that day. And some days it tries to extend upward and just stops at a very shallow level here. Those are shallow cumulus. They can't build very high. And some days they're able to build deeper. So those are deep cumulus. They're able to bubble up further from deeper through the atmosphere. And on some days, they can extend all the way up to the tropopause. So they can extend as high as the tropopause. So in that case, you would have a cloud that has its base down near the ground, but actually builds its way all the way up through the troposphere, all the way up to the tropopause, and usually a little bit into the stratosphere in many cases. So what are these guys made of? Well, it's kind of the same deal as before, that in the lower troposphere, they're mostly water. And then as you go up, you get more ice. There might be some mixed ice and water in mid-troposphere, and when you get to the upper troposphere, they're mostly ice. Where this transition happens between water and ice depends on the season and the latitude. Here, where it's fairly warm much of the year, you could think of in sort of late spring when these clouds are forming is when they're most common, or the deep ones anyway. And the transition might be something like 4 or 5 kilometers, something like that. Once it gets up above that, below that level, it's mostly water. Once it gets up higher than that, it gets pretty cold, and so it turns to mostly ice, sort of in the upper part of the cloud. So the forms that cumulus clouds can take, well, they tend to have this puffy appearance, and if they don't develop very deep, if they're restricted in how deep they can develop on that given day, we'll talk why that it would be later, what sets how deep they can go. But if on a given day they can't build very deep, then they kind of have this cotton ball appearance that we see all the time around here in the summer. But then on other days, they look more like plumes of air that bubble up from below. And so that's what you see here. These guys in this bottom figure are actually referred to as towering cumulus. Technically, they're cumulus congestus. And so these guys are actually warm plumes of warm air that are bubbling up from below. That's exactly what they are. We'll show more examples of that on the next couple slides. These guys up here that don't build upward very high, these guys are often referred to as fair weather cumulus. They tend to form on days when you're going to have, unlikely to have storms develop. And these guys are called fair weather cumulus, or technically they're called cumulus humilis. Cumulus humilis. Okay, so those are our basic cloud types at any rate. Now, within each of these main categories, cirrus, stratus, and cumulus, they subdivided into a number of different subcategories depending on the characteristics of the cloud. And if you want to go through and learn all of those, by all means do it. We're not going to talk about any of those things moving forward. All we really need to know are the basic distinctions, and so that's what I'm going to focus on. But again, the pages and the text that are listed on the website are a good place to start if you want to learn more about that. Okay, so now let's talk a little bit about when these different kinds of clouds form, and a little bit about why that is. So let's start with cumulus clouds. This is the one we're going to focus on mostly because this is going to be the type of cloud that can lead to thunderstorms. And cumulus clouds are clouds that form in conditionally unstable environments. So this is tying back into this notion of stability that we talked about in the last screencast. If you remember, there are three different categories of stability. There's stable, there's unstable, and there's conditionally unstable. And conditionally unstable in particular was this category where the air will continue to rise. It's unstable and it continues to rise, but only if it's saturated. That is, only cloudy air will continue to rise. And this is the kind of environment that you typically tend to see cumulus clouds. You can also see cumulus clouds in unstable environments, but they just don't happen that often. So you're more likely to see them in the conditionally unstable case. And the reason that they form this way is that basically cumulus clouds are plumes of warm, saturated air. That's what they are. And so in a conditionally unstable environment, once the air becomes saturated, it'll end up being warmer than the air around it, and it'll want to continue rising. You'll end up getting this kind of thermal that bubbles its way upward. And as it bubbles its way upward, it takes the form of a cumulus cloud. That's exactly what a cumulus cloud is this saturated air that's warmer than the surroundings and bubbling its way upwards. So that happens in conditionally unstable environments. So if you're looking at this, for instance, this is an environment that's pretty unstable. There's a lot of these little clouds that are bubbling their way upwards. But each one of these cumulus clouds here that's extending upwards is really a plume of warm air that's bubbling upwards. And the reason it's warm is because it's saturated. You've got condensation going on, which keeps it a little bit warmer. And so it's warmer than the surroundings, and it rises. Here's another example. So this is the same one we saw before. We've got three towers sort of here building upwards. 1, 2, 3. And each one of these guys is a plume of warm, saturated air, warm, cloudy air in a conditionally unstable environment. So it ends up warmer than the surroundings and it keeps rising. And that's the kind of form you get then. You get this thermal bubbling its way upwards. And on some days, if it can bubble its way up deep enough, then you get something like this. You get thunderstorms. Thunderstorms are just going to be big old cumulus clouds that consist of warm, saturated air that's bubbling its way upwards. In this case, it's extended upwards through most of the troposphere. We're looking at this from a distance, but this is a very deep cloud that goes up way to the upper troposphere here. So you've got this plume of warm air extending upward here, sort of on a slant in this case because it's developed its own structure. But that's what it is, a plume of warm air extending upwards. Now, there is one caveat to this, because if you're looking at a cumulus cloud, say if we go back to these guys here, the air that's feeding into the cloud and bubbling upwards down here is actually not saturated. That's dry air. It's not cloudy air. And so that air is not in a conditionally unstable environment. It's dry. And remember, dry air doesn't want to rise. In a conditionally unstable environment, it'll rise, but only if it's saturated. And since this air down here isn't saturated, it's not cloudy, it actually doesn't want to rise. What this means in practice is that in order to get a cumulus cloud going, you're going to have something to take the dry air down here below the cloud and push it upwards until it's saturated. Once it's saturated and becomes cloudy, then the conditional instability kicks in and it'll rise on its own. But you're going to need something to push it upwards to get that to happen, because the dry air doesn't want to rise. This thing that pushes the air upwards until the cloud forms, that's called the trigger mechanism. The trigger mechanism. We're going to need some trigger mechanism to lift the dry air to the point where the cloud forms. Then conditional instability kicks in and the cloud goes by itself at that point because it's warmer than the surroundings. This trigger, this thing that lifts the dry air to the point where it becomes saturated and the air rises on its own, can take the form of a variety of things. It could be a front that passes through and lifts the dry air till the cloud forms, and then it continues to rise. It could be a dry line. We haven't really talked about dry lines, but they're kind of like fronts. Just instead of change in temperature, it's really a change in humidity. It could be a warm thermal. So you have a warm spot at the ground, and that causes the air to rise at that spot until eventually the cloud forms. It could be a wave that propagates through that causes the air to rise. Low-level convergence into a low-pressure system, say, or other kinds of convergence will push air upwards and cause the air to rise. Flow up a mountain. There's a variety of different things that can lift the air while it's dry up to the point where it becomes cloudy, and then it starts to go on its own because conditional instability kicks in. So here's a figure from the text which shows kind of what this might look like with numbers on it here. It's kind of a complicated figure. Basically what's going on is we've got height here on the vertical axis. 1 kilometer, 2 kilometers, 3 kilometers, 4. And we've got over here, this is the temperature of the environmental air. So this is the surroundings, if you like. This is just whatever air was at that height, when we came along that day and looked upwards. That's the temperature of the air that was already there. And you can see that it was 30 degrees down here at the ground, 21, 12, 3, and -6. So the temperature was decreasing as you go upwards. And it's decreasing by, at least initially, looks like all the way through, it's decreasing by 9 degrees per kilometer. And a temperature decrease of 9 degrees per kilometer is actually conditionally unstable. Conditionally unstable, meaning that dry air, again, doesn't want to rise, but the cloudy air will. So the way this works then is if you have dry air below cloud base, you're going to have some mechanism to lift it up because it doesn't want to rise. So that's our trigger mechanism. So we need some trigger to lift the air until it's saturated and becomes part of the cloud. Now in the book here, from the sketch from the book, they've set the trigger mechanism to be a helicopter, which of course is ridiculous. But it could be any of these mechanisms that we talked about before that would cause the air to lift a little bit until it becomes saturated and continues to go. But you'll note that when we take this air down at the ground and I lift it 1 kilometer, based on the previous screencast, for every kilometer it goes up, and at this point it's dry, Every kilometer it goes up, it cools by 10 degrees. And so when you get up here at 1 kilometer, the temperature is 20 degrees. But if you compare that to the temperature of the surroundings were 21. So it ends up being colder than the surroundings and wants to fall back down. So this just reflects this idea that in the conditionally unstable environment, the dry air doesn't want to rise. It's colder, and so it wants to fall back down. So you need a trigger to push it up. So at cloud base then, the air is still colder than the surroundings. So just when it gets to cloud base, it's colder than the surroundings. That's why you need the trigger to push it up. But then, once it becomes saturated, then it doesn't cool as much because of the condensation. Condensation keeps it a little bit warmer. And so instead of cooling 10 degrees per kilometer, now it's cooling 6. So by the time we get up to 2 kilometers, we started at 20 at cloud base, it cools 6 degrees, and we end up at 14. And if you compare the temperature there, inside the cloud, to the temperature of the surroundings, it's actually going to be warmer at this point because the saturated air stays a bit warmer. And so once the air becomes saturated, once it becomes part of the cloud, then the air becomes warmer than the surroundings, and it rises on its own at that point because it's warmer than the surroundings. It'll just keep going. So that's how it works. So you should probably sit and look at this and just sort of make sure that the numbers here make sense. The environmental numbers are just whatever they are. That's just what it looked like on that day. Those were the temperatures at those levels on that day. The cloud numbers, though, these guys are determined by how much the air cools when we lift it. And remember that dry air cools 10 degrees. So that's why it started at 30 and ended at 20. But at this level, it hit the cloud. It was in the cloud, and so it's not dry anymore. So when it was dry, it cooled 10. Once it becomes part of the cloud, it only cools 6 degrees per kilometer. And so if it's at 20 at cloud base and it cools 6 degrees, then it's at 14 once it gets up to 2 kilometers. So make sure that those numbers sort of make sense and so that you understand where those numbers came from. And then when you compare them to the surrounding air, you can see that you needed the trigger initially to push it, but then it became warmer and kept on going. In any case, the end result of this process is that what you've got is you end up with this plume of cloudy air that's ascending through the atmosphere. And the reason it's ascending is because the cloudy air is warmer. Now, we know from experience, though, that these clouds don't always develop all the way up. Sometimes they stop at different levels. And so why is that? What determines how high these clouds are actually going to go? Well, what determines how high these clouds are going to go is just what the stability looks like at different levels in the atmosphere. As long as the stability remains conditionally unstable, then the cloudy air will rise. But if it happens to hit a layer where it's stable, if we happen to hit a stable layer, remember stable means that the air always wants to sink. It always wants to fall back down, regardless of whether it's cloudy or not. So dry air falls back down, cloudy air falls back down as well. And so the cloud, once it hits the stable layer, it just won't go any higher. So it might look something like this. Let's suppose on a given day, we have an environment that down here in the lower part is conditionally unstable. It's unstable for cloudy air. And then above that, we've got a layer that's stable, which means that everything falls back down. So what's going to happen? Well, if we form a cloud, that cloud's going to be able to extend through the conditionally unstable zone, because as long as it's conditionally unstable, it'll keep rising. But when it hits the stable layer, it'll stop. And so your circulation into the cloud might look something like this then. You've got air feeding into the cloud from below, kind of like that. And once that air gets into the cloud, it'll continue to rise. But once you hit the stable layer, stable means that the air falls back down regardless of whether it's saturated or not. And so once it hits the stable layer, it falls back down. So if we sort of go through and characterize what the air is doing, below cloud base where it was dry, we needed a trigger mechanism to push it up. So that's where our trigger comes into play. Down below, because it's dry, it doesn't want to rise. Once it hits the cloud and becomes saturated, then it'll rise freely on its own as long as the environment is conditionally unstable. So for this part of the cloud, it's freely rising on its own because it's warm, until it hits the stable layer. In the stable layer, the air always wants to fall back down, and so when it hits there, regardless of whether it's cloudy or not, it sinks back down. So it sinks back down once it hits the stable layer. So what's going to determine the depth of your cumulus cloud then on any given day is just wherever these stable layers set up, and that can vary from day to day. Often around here, it's in the summer, like days like around now, it may be a kilometer or two where you'll hit sort of a stable zone. And that's why you'll get those little cotton ball clouds forming right at that height, because as they ascend, they're going to hit the place where the cloud forms, and then they can't go much higher because there will be a stable zone that inhibits them from going much higher. Okay, so that's how cumulus clouds work. Now again, that's what we're going to focus mainly on because that's the type of cloud that can form thunderstorms. And that's what we'll start doing with the next screencast. But let's at least mention how it is that we get stratus clouds as well. So cumulus clouds were clouds that formed in conditionally unstable environments. They're warm plumes. Stratus clouds are actually clouds that form in stable environments. Now, you might ask yourself, how can that be? How can you get the clouds in the stable environments? Because in stable environments, the air wants to sink back down. And the answer is that you're going to get the air to rise in a stable environment only if you push it upwards. That is, you have to have forced ascent. You have to have some process pushing the air upwards. Otherwise, it won't rise. Stable environment, it wants to fall back down, so you have to push it upwards. In that sense, it's kind of like the trigger. But the difference here is that typically when you have a stable environment and you're causing forced ascent, most of the mechanisms that do that actually cause forced ascent of a whole layer at once. So you're taking a whole layer of air and pushing it upwards against its will because it's stable. But if you push it upwards, it'll go, and that's how you form stratus clouds. Let's maybe sketch that out down here at the bottom. So let's put the ground in here. Oh, that's interesting. One of my little ticks got off here. Well, it doesn't really matter. And let's suppose that the typical way this will happen is convergence into a low pressure zone. So let's go ahead and consider that case, convergence into a low pressure zone. So let's say we've got a low center here in the middle. And let's say we've got air converging into that low center. Now, you'll remember that the air doesn't just converge into the low center. It really swirls around the low center counterclockwise. So if you've got a cyclone, it circles around it counterclockwise. But because of friction, there's a tendency also to cross the isobars in towards the low. And so you end up with some amount of convergence in towards your low here as well. So you can think of this air as circling around the low here, sort of into the page over here and out of the page over here, so as to give you a counterclockwise circulation. But at the same time, there's a tendency to draw into the low, and you produce some convergence. Now, as we mentioned before, if you have convergence into a zone like this, it's kind of like squeezing the bottom of your tube of toothpaste. And so you're going to take the air that's there. As this air converges in, the air that's already there is going to get pushed upwards. And so that's what we mean by forced descent. That convergence is pushing the air upwards. But you'll note that the convergence doesn't just happen right in the center of the low. It's actually happening all along here because you've got faster air and it sort of collides into the slower air, which then collides into this even slower air. And so all along here we're converging air into each other. And so because of that, you're pushing the air upwards all the way through here. So through that whole zone we've got convergence going on. And as this faster air converges into the slower air, it's going to take some of the air that was in between and push it upwards. And so you end up with this whole zone of air that's being pushed upwards. This is what I mean by pushing a whole layer of air upwards at once. We're taking this whole region around the low and pushing the air upwards. And note that this will happen even if it's a stable environment. Even if the environment's stable, if you've got convergence going on down here, it'll push the air upwards. It's called forced descent. It's not rising on its own, it's being pushed upwards. And of course, if you have enough water vapor in the air, then as this layer of air is pushed upwards, then eventually you'll hit condensation and you'll get a cloud forming. Since you're pushing the whole layer of air upwards, you're going to get a layer of cloud to go along with it. And that's how stratus clouds form. So forced descent results in stratus clouds, layers of clouds that formed as the whole layer is lifted. Okay, so that's our basic description, our basic discussion of cloud types and how the different types form. In the next screencast, we're going to transition and start talking about thunderstorms a bit.